Hi everybody, this is lesson 3.6, the final lesson in modulus 3, and we're going to talk about something that's called normal distribution. It's the last topic in statistics that we'll cover in our course. So let's read the specific objectives. So students will understand that certain phenomena follow normal distribution. The standard deviation allows inferences about certain populations, and students will be able to recognize the normal distribution and use something that's called 68, 95, 99.7% rule. All right, let's begin on looking at this. Now, notice in the objectives, you do see standard deviation being stated. So I would like to first ask you what the standard deviation measures. Okay, so standard deviation measures an average difference or deviation from the mean, where the data is located on average, how far away. Keep that in mind because that will be used in this lesson. All right, let's read the problem situation number 1. What is normal? We have Diego, who's finishing his last semester at the Baruch College, is pursuing a Bachelor's of Business Administration, BBA degree. And he is also considering continuing his education at a business school. He wants to pursue a Master's of Business Administration degree, or MBA, from a good school. The Graduate Management Admission Test, GMAT, is a computer adaptive test that is used by most business programs to select its students. Based on the previous statistics, getting into a good business school required scoring in the top 15% on that exam. Diego wants to know what score he needs to get to have a chance. The GMAT is scored between 200 to 800 points, and figure 1 displays the score distribution on GMAT. Okay, so this is the the distribution. That's how the picture looks like. And the first question is asking us that the vertical axis is not labeled. Vertical is this. All right, and the question is, what do you think it could measure or represent? I'll give you a moment. All right, so the vertical axis here represents how many students or how many test takers are scored in a given range. So for instance, if I look at 460 and I'll look up here, and labeling is missing here, so we don't know what those numbers are, but it gives me an idea of how many people are in that category. Even though we cannot see an actual number, we can see that people who scored in that category is lower than people who score, let's say, 500. Okay, the term that we use to describe this height, the position of how many observation we get in a particular category, is called frequency. And the frequency can either represent the number, let's say 1,000 people, 2,000 people, or sometimes it can represent a percent, like how many of all the people scored in that particular category, and so on. So that's what goes in a vertical axis, frequency. So let's move on. Let's try to understand this diagram better. So frequency, or something that's called a relative frequency. If you remember the term relative from the relative change, that has to do with the percentage. Okay, and frequency is just a raw number, the absolute number of people in whatever category. In 1 or 2 sentences, describe what the above chart says about the overall score results of the GMAT. So how can you describe this, what you see visually? What would you say? I'll give you a moment. Alrighty, so let's review. Well, it looks like that the scores peak somewhere here. It's not clear exactly what it is, but it's somewhere around maybe 5, 4. Like if you look at the range here, this one is 538, this one is 550. So that looks like it's a 12 unit difference. So maybe it's like 6 units each. So maybe like 544 or so. That would be that number. So it looks like the middle number is 544, and it looks like it decreases as you go to each tail. So that's what you could say. So if you want to write something that would describe the distribution, we can say more score. How would we call these are not students, the more test takers scored in the middle of the score range, because it goes between 200 and 800. So about what number is in between? It looks like it's around 544. More test score in the middle of the score range, or around a range. You can say around 544. Okay, and the amount of scores to the right or left of the peak are decreasing, are gradually decreasing. All right, so that's how we can describe this, right? So we got the peak around 544, and then it goes down as you go to the right and to the left. Notice there are very few test takers who get a perfect score, and there are few who also get very low scores. So, that's what we kind of observe. Now, to give it a little bit more precise terminology, the distribution that we just seen in figure 1 comes from making a histogram of many thousands of GMAT scores. Remember the histograms that we did early in the modulus to see how many people were in each category? Well, when there are many observations, a histogram will appear as a curve instead of a series of vertical bars, and the scores on the GMAT follow a so-called normal distribution. A normal distribution is a bell shape with a peak in the middle and a tail on either side. So that's how the normal distribution would look like ideally. So there's a peak and then it levels off. You might have heard the term a bell curve. Okay, so that's what it is on normal distribution. It has tails and it has a peak in the middle. The mean of the data as well as the median will be right in the center. And this type of phenomena with that type of distribution is common in everyday life, in nature. For instance, people's heights, weights, heart rate, blood pressure, etc. follow a normal distribution. A lot of physical characteristics follow a normal distribution. And why are we bringing it up here? Well, there's something that was discovered at the end of the 19th century, and that's a relationship between something that follows normal distributions and expectation of how of what would you see as you go away from the peak. And here's what it says: approximately 68 of all the observations fall within one standard deviation of the mean. Approximately 95% fall within 2 standard deviation, and approximately 99.7% fall within 3 standard deviation of the mean. This is what you see on this diagram, and that is called a 68, 95, 99.7 rule, also known as empirical rule. So let's understand what that is. You see those numbers right here, 1, 2, 3? Those are standard deviations. Remember last lesson, we looked at commuting time, and we got that commuting by bike had an average on 44 and the standard deviation of 2. Remember that example? So then if you look at that example, and I draw a picture for you, if the distribution was normal, and I believe it was, we didn't define it back then, but it was a normal distribution if you were to collect more data points, you would see that type of shape. That means most of the time it would have taken Melissa 44 minutes to commute to work, but there will be some deviation from that. But that deviation is measured by the standard deviation. So if you go one standard deviation, it's going to be 46. If you go one standard deviation that way, it would be 42. So standard deviation, the average was 44 minutes in that lesson, and the standard deviation was 2 minutes. So basically, if you make a step to the right and a step to the left with the size of standard deviation, all right, then listen to this. This will make it very clear. Once you make that step, that means 68% of the time when she commutes, 68% of every whatever she commutes, 68% of the time her commute will be between 42 and 46 minutes. All right, so 68% of her commute times would fall between 42 and 46 minutes. I mentioned last lesson is that, we already did. And remember we used the words like within, give or take, 2 minutes. So now, instead of just saying give or take, we say that there's a 68% chance that her commute will take that long. All right, so that's the most common event. Now, if you make another additional step, and listen to this, if you make another 2 minutes, so it's 48 and 40, and notice the standard deviation is not that large, it's only 2 minutes. Now, that means that 95% of her commute, times, will fall between 40 and 48 minutes. So that means we can say with 95% confidence that it's going to take her between 40 and 48 minutes. So that way, she would know when to leave and never be late. All right, you just take an extra 10 minutes to your commute and then you're good. You will never be late just because of this statistical observation, which is pretty powerful. All right, so let's go back to our GMAT scores. So the GMAT scores in 2016 averaged 552. So that's the average score in that year, with the standard deviation of 121, which is a pretty large standard deviation. But, still, it gives us an idea of how the scores are spread. It's asking us find the range of the score achieved by 68% of all the test takers. All right, based on that rule, assuming again that the GMAT scores follow the normal distribution. So I'll ask you to take a moment and, using this idea, which we just discussed, pick a choice that will give us the 68% of possibilities. I'll give you a moment. All right, so let's review. 68% is within one standard deviation of the mean. So what that means, guys, is you're going to take 552 and you're going to subtract 121, and then you take 552 and you add 121. See, you add and subtract the same standard deviation, and that will give you the scores of 431 and 673. So that's where the 68% of the students will score. You see, once we know that information, we can say a lot about those test takers. Alrighty, now let's think critically. Okay, so the next question will be a little bit, will require a little bit of more understanding of what this all means. Based on the above, approximately what score do you think Diego needs to get into a top business school? Well, in order for us to answer this question, we need to go back into our original problem situation and find out what was he trying to achieve. All right, so he wants to be in the top 15% of the GMAT scores. Top 15%. All right, so top means higher scores. All right, so let's see. So we want top 15%. So let me help you to scaffold this a little bit for you, since this is new to us. We're going to make a picture, all right? And then we're going to try to identify where is the top 15% located. All right, so let's go. So we just determined 68% of the distribution, correct? So this was 552. So if you make one step to the right, that's 673. And you make the one step to the left, which is 431. This, let me highlight this for you. This area right here, this region, that's where 68% of the test takers will fall, right? So that's 68. Now, what about the rest? Well, there's some property of this normal distribution that is completely, that the curve is completely symmetric. That means that right here cuts distribution into two equal parts. Alrighty? So what does that mean? So check this out. The whole thing, the whole distribution, the entire distribution, this whole thing. The curve, by the way, theoretically, we don't go into details in this class, but the curve goes indefinitely, so it goes forever. We say anything is possible, but for the purposes of this, basically this part, okay, and this part are going to be identical. They both are going to be equal, correct? So if this is 68% and this whole thing is 100%, then the blue area, this blue region, the blue area, let me just highlight it like that. The blue area is going to be 100% minus 68%. That gives us how much? 32%. All right, so that means that together, this region and that region together gives us 32%. Okay, you understand the whole thing is 100. In the middle is 68, so it leaves us 32 to each tail. So it's for both tails. And since the this distribution is completely symmetric, that means 32 divided by the 2, which equals to 16%, will be the bottom 16%, and the other 16% is going to be the top 16%. All right, when you're dividing it. So in other words, you will have 15% here, 16, and you got 16% here, so it's the bottom 16. So we want to know, what will get his in the top score. Well, to get to the top 16%, his score got to be 673. So it needs to be, so it must be higher than 673 in order to be in top 16. Now, if we want to go further, and let's say if you want to be in the top percentage, that means you want to do another step. So if you make another step, 2 standard deviations, so if you start with the 552, and you make one step, gives you 673, that was the standard deviation is 121. Make another 121, well, you're already getting to the very high scores. So that would be 794, almost a perfect score. That will be right here. What's left right here? It would be 5%. I don't know if you could see it. Let me move it right here. 5% divided by 2. So this is the top 2.5% of test takers, and I would probably say that in reality that percentage is even lower than that. But what I'm trying to just for you to understand, we're not going into details of this. Something like this you study in the course of statistics, but in quantitative reasoning, what you want to understand is when you go away from the average, okay, and your step size equal to the standard deviation, the probability or percentage of people who will be in that category, or the percentage of scores or percentage of whatever, is going to decline, and we can actually predict what those percentages are. All right, let's practice a little bit here. Each of the following scenarios involve a normal distribution of data. Use the mean and standard deviation to assess each statement. So the average temperature in New York City in the month of July is 75 degrees Fahrenheit with a standard deviation of 7. This July, the average temperature was 82 degrees. It was an exceptionally hot this July. So what I would like for us to do, can you give me the range, okay, of the temperatures that happen 68% of the time? 68% of all temperatures in a month of July. Sometimes it's, instead of say all temperature, you say 68% possibility or likelihood for the temperature in July to be 68% of all temperature in the month of July falls between, and then I'm going to ask you to give me the two numbers based on the fact that the average is 75 degrees and the standard deviation is 7. So can you go ahead and fill out those two temperatures? I'll give you a moment. Alrighty, so let's review. 75, so you do 75 minus 7, that gives you the bottom range. So that would be 68 degrees Fahrenheit. And then if you add 7, that gives you the 82 degrees Fahrenheit. So that's the bottom temperature. So this what will happen most of the time, 68% of the time, which is almost 70. So if the average temperature was 82 for the whole month, then that means that most of the time the temperature was in 82, like around 82. This is very unlikely because, you know, if you expect the temperature to range between 68 and 82, right? And then the average ended up being 82, that means that most of the days it was pretty hot. Do you agree? So this will be unlikely. So that statement is definitely true. Okay, in statistics, you learn more about the likelihood of the average, what it could possibly be. It's called the essential limit theorem. You study that in statistics. But for us, just understand, if you're given information that the average is 75 and the standard deviation is 7, that means that temperature falls between 68 and 82. That's what's gonna happen 68% of the time. All right, so that gives you the range of expectation. All right, so let's look at another example. College students sleep on average 7 hours per night with a standard deviation of 45 minutes. Note hours and minutes. The units do not match, so be mindful of that. Diego gets around 5 hours of sleep each night. Diego thinks that he sleeps a bit less than normal, but not especially so. All right, so here what I would like for you guys to do. Can you write what is 68% of college students what do we know about their sleep? So 68 of college students sleep between, and I would like you to give me the two numbers. All right, first, all right, where the average is 7 hours and standard deviation is 45 minutes, and I want you to write the answer using hours and minutes, okay? So you got, I'll give you a moment. All right, so if you review it, let's review it. So you got 7 hours minus 45 minutes. So that would be 6 hours and 15 minutes, correct? And if you add 7 hours plus 45 minutes, then you get 7 hours and 45 minutes. So that's what's going to happen 68% of the time. All right, how about doing one more? All right, so let's do, I want to ask you to do the same thing, but now with 95% of college students. All right, so we're expanding the range. So look, when you talk about 95%, then you got to make two steps. and then we'll assess where Diego falls. So 95. How we're gonna do this? We need to take and subtract 45 twice. Okay, so we can do it, right from the beginning, just as a practice, right? So you subtract 45 twice. So that means you're subtracting 90 minutes, correct? 90 minutes is 1 hour and a half, right? So 1 hour and 30 minutes. So if you subtract this, you're going to get 5 hours and 30 minutes. So that would be the lower end. And then the upper end is going to be 7 hours plus 1 hour and 30 minutes. So that gives us 8 hours and 30 minutes. So look, a little bit of time calculation, but the understanding here is once we subtract the standard deviation twice and we add the standard deviation twice, that tells us where majority of college students will fall. All right, now where the Diego falls, he said he sleeps 5 hours. So 5 hours will put him outside of 95%. So outside of 95% is very unexpected. I mean, it's not typical, right? So he definitely undersleeps. So it's pretty far away, okay? Pretty far away. Do you understand? Do you see it's outside of that? Now, there is something that you could do to measure this without finding 68% and 95%. That's something, again, goes a little outside of what we need to be able to do, but you can calculate something that's called a z-score. And the z-score measures how many standard deviation is a given observation away from the average. Okay, so what you do is you take the Diego's sleep time, which is 5 hours, you subtract 7 hours, and you divide it by standard deviation, which is 45 minutes, but 45 minutes is what? It's 3/4 of an hour, so it's 0.75. Okay, and if you subtract that, 5 minus 7 gives us 2, -2, and then when divided by 0.75, it gives us -2.66, repeating. That tells us that his sleep time is far away from expectation. I'm not going to ask you that to calculate the z-score, all right? Again, we're not in the statistics class, but if you ever take statistics, that's what you study. All right, what I will ask you is to write out those percentages. All right, what happens 68% of the time? What happens if 95% of the time? That's where you understand that you have to add and subtract the standard deviation. 68% you do it once, 95% you do it twice, and 99.7% you do it 3 times. And our final, we have 2 more questions. So number 7. Mark is 16 years old. He loves playing video games. He plays on average 6 hours each day. Mark's mother is concerned that he's playing way too much. Mark disagrees, saying 1 out of every 3 kids my age spends even more time playing video games than me. How can it really be that bad? And now teenagers, Mark's age, play on average 5 hours with a standard deviation of 90. All right, so once again, we're going to look at the statistics. All right, so 5 hours is the average. And let's write the standard deviation to make it less confusing. 90 minutes is an hour and a half. All right, so it's 1.5 of an hour. Let's write it in hours. This will be easier for us to to define the range. So he plays on average 6 hours. So let's say, where does he fall? So once again, what I would like you to do, let me this time draw the picture, just so we remember that we talk about normal distribution. So right there, the average is 5, standard deviation at 1.5. So what I would like you to do is, once again, make that one step. All right, so do 68%. 60% of teenagers, Mark's age, or 16 years old, they play between what two numbers? So where would it fall? And we're talking about weekly, right? Does it say weekly? Oh my gosh, no, not weekly. It's daily. So as much as sleeping, basically. All right. So what happens? 68% of teenagers. How many hours do they play weekly? And I believe this is a real statistics. So yeah, I wish it was the time spent doing my homework, perhaps, right? But I'm biased. Anyway, so 68% of the time we need to do what is it? One standard deviation step. All right, so let me give you a moment to make that step. Alrighty, so let's review. So if you go to the right, you're gonna have 6.5 hours, and if you move to the left, you get 3.5 hours. All right, each day. All right, so that's where the 68% of the people fall, teenagers of 16 years old. That's how much they play. You see, that's the concept of today, is that you can say now the percentage. Not only you're going to say, okay, what do I expect, but I can also say it's 68% of those people. Now, where does Mark fall? So he plays 6 hours. So 6 hours falls right here. So he is within a green zone. So he is actually telling the truth. Now, can we make this a little bit more precise? Like he says that 1 out of every 3 kids my age spend even more time playing. Well, in order for us to see like where does he fall, you can go ahead and again, just for your knowledge, you can calculate the z-score. So this is basically to see how far he is from the average. So look what we're doing. You do 6 minus 5, and you're dividing by 1.5. So that falls 1 divided by 1.5. It's 0.66 repeating. So he is within 1 standard deviation. So that gives us a good idea is that where he is, and he is telling the truth. All right, and finally, the last question. An IQ score is a measure of person reasoning and problem-solving abilities. The average IQ score is 100, standard deviation is 15. We have Rajgari Pawar, a 20-year-old girl from Great Britain. She has an IQ of 162. She must be a genius, since genius is considered someone who is smarter than 99 out of 100 people. Based on the IQ score, well, let's see where, again, where would one fall. So we're going to do the distribution. All right in the middle, you have an average of 100, and the standard deviation equals to 15. So let's make one step. All right, so that would be 115. Let's make the second step. That gives us 130. And then let's make one more step. So that's 1 standard deviation, 2 standard deviation, and a 3rd standard deviation would put us at 145. All right, so that would be, and you can also go to the left. So 85, 70, and 55. Right? Did I do the math right? Okay, so that gives us right here, that's 99.7% of the people, of everybody, 3 standard deviation. All right, she is 162. So she's right here. So she's even more than 4 standard deviation. All right, so she's definitely there. So it's not just 99 out of 100 people. The only thing that's left right here, all right, is 0.3%, because the whole thing is 100, divided by 2, which is what is it? It's 0.015 of a percent. And I think I even calculated a fraction somewhere. Yeah, so this one is going to be actually 0.15%, which is 0.0015, which equals to 15 out of 10,000, which reduces to 3 out of 2,000. So 3 out of 2,000 people fall in this particular category. All right? And she's even further than that. Okay? So that's the idea. Again, it gives us the range of expectations. So hopefully you get this connection. Alrighty, on this, we're going to finish the last lesson of this chapter.